All right, so in this little mini lecture, I just want to look at some examples of oscillating motion from section chapter 14, section 3. And first problem here says the motion of glider on a spring of a glider on a spring. An air track glider oscillates horizontally on a spring at a frequency of 0.50 hertz. So I'm just going to jot that down. That's the same as saying 0.5 cycles per every 1 second. A cycle is there and back. So it's going to tell us that suppose the glider is pulled to the right of its equilibrium position by 12 centimeters. So we have something like this. Maybe this is equilibrium here at 0, and the glider is down here on the air track or whatever this is on, and it's pulled. The spring is stretched 12 centimeters, right? So this is this distance right here. You could say its position is positive 12. So I'll just write that down here. So this is its amplitude, is what I'm trying to get at. Its amplitude is 12 centimeters, right? And where will the glider be 1 second after it's released? So when it's resting, it's here at this 0 position, and right now it's at position positive 12. So 1 second after it's released, well, we can see just by looking at the frequency up here that it will travel 0.5 cycles in 1 second. So a cycle, if I switch colors here to maybe green, a cycle is for the time, or is not even the time, a cycle is just there and back. So there, if it's starting with an amplitude of positive 12 centimeters, it's going to go all the way to negative 12, right? And then all the way back. And that's going to be what a cycle is. So let me get that in black. So all right. So then if it goes 0.5 cycles in 1 second, then it just travels there. So where will the glider be 1 second after it's released? 1 second after it's released, the glider would be at negative 12. So our first answer would be 12 centimeters. We could say negative 12 centimeters. I'm going to say instead, I'm going to relate it to equilibrium. So I'm going to say 12 centimeters to the left of equilibrium. And then what will its velocity be at this point? So we know that when it's at a max position and amplitude, it's actually it's stopping because it's turning around, right? So right here, when it gets to negative 12, it's about to turn around for this return trip in blue, which is going to be to the right. So it needs to go from that black vector to the blue vector, from having a velocity to the left to a velocity to the right. Negative velocity to a positive velocity. So we expect at this point, it's going to be a turning point, and it's going to have 0 velocity. So velocity is equal to 0 meters per second. All right, and I can just write at this point. All right, and that's pretty much it. I think in the textbook, they go ahead and make a wave, like we worked on a sinusoidal wave, and they have the positive 12 being the amplitude, or 12 centimeters being the amplitude, and so positive 12 and negative 12. If we want to put that in meters, We can, do we have to? It wouldn't hurt. So maybe I'll say positive 0.12, and this is its position, right? X meters. So positive 0.12, negative 0.12, and then the object is going to travel, let's see here. So I think the way we like to draw this was we had t over 4, t over 2, was it 3/2 t, right? Do I have that right? No, I have that wrong. Let me erase that. 3/4 t. Yeah. Geez, I'm thinking radians. And then t. And we said that if I draw this wave and say blue, we said that it would start right here at positive 12, and at t over 4, it would be at 0, right? Because we know this is going to be a positive cosine wave, and then at half of the cycle, right, to go there and back, this is when it hits negative 12, which is right here at half of the period, and then right here, and then back to the very beginning. So something like this. Try and draw this sinusoidal wave. Okay, so this is another way to look at it. What is the period? Period is equal to 1 over f. So if you wanted to calculate that, you could. It's just 1 over 0.5. 0.5 goes into 1 how many times? We would just say 2. So the period here is t is equal to 2 seconds. So we can see that if it takes 2 seconds to go there and back, then in 1 second, where will it be? It will be at its negative amplitude, and that makes sense. So it'll be at negative 12, and we can see that point, or negative 12 centimeters, negative 0.12. We can see that point in orange right there that I'm highlighting. Okay. So there we go. Let's go and look at the next one. Measuring the sway of a tall building. The John Hancock Center in Chicago is 100 stories high. Strong winds can cause the building to sway, as is the case with all tall buildings. On particularly windy days, the top of the building oscillates with an amplitude of 40 centimeters. Let's go ahead and jot that down. I don't know if we're going to have to know the height of 100 stories, but I'm just going to kind of mark that right there. The amplitude is equal to 40 centimeters, which we might as well just go ahead and convert it to meters, 0.4 meters. And a period of 7.7 seconds. What are the max speed and acceleration of the max acceleration of the top of the building? All right, so to find this, right, all we're gonna do is go ahead and use those formulas we know, right? So what we saw in the notes there was that Vmax is equal to 2 pi f times the amplitude, and I think we said A max, or position max, right? Which we said is just equal to A. Notice they increased by a factor of 2 pi f every time. And then we said A max, acceleration max, is equal to 2 pi f squared times A. Okay. So, anyways, to get Vmax, then we just need to know the frequency. So let's come back up here and find frequency. Frequency is going to equal 1 over the period. So that's equal to 1 over 7.7 seconds, What is that equal to? Hold on. I'm getting 0.129, so like 0.13 hertz, or you can say 0.13 cycles per second. So this is interesting, just thinking about this, right? That this building is going to move 40 centimeters, or have an amplitude of 40 centimeters. So 40 centimeters one way, back to 0, and then 40 centimeters the other way, oscillating back and forth over, which seems like a lot, and it is, you know, for a big building like that. I mean, to be moving, you can think about it, it's almost half a meter stick. So I guess maybe it's not too much for a big building, but at the same time, like, it is over 7.5 or 7.7 seconds. So it's quite a long time. So do you notice it? I don't know. You know, I doubt it. But I'm sure it's detectable in some ways. All right. So anyhow, coming back down here to Vmax, that's a good question, but probably not. But there's probably little ways you might notice it. Is what I'm trying to say. Okay. Vmax equals 2 pi f times the amplitude. Some of these problems, when we use sine and cosine, we have to set our calculator into radians, but not in this one. We're not doing any sines or cosines here for the maxes. If we had an equation for velocity or acceleration, we would have to. So we have 2 pi times the frequency, which we said was that 0.13 hertz. And the amplitude was the 40 centimeters, so 0.4 meters. And what does that end up equaling? I'm going to go ahead and write it up here. Let me go ahead and plug it in my calculator. Looks like I'm getting about 0.327. So 0, let me see. This is Vmax. 0.327 meters per second. Sound right? It sounds pretty dang fast. It is at the maximum. All right. So I'm good with that. It seems like that would be noticeable. 33 centimeters per second. Okay. And then the acceleration, but I guess that would just be at one point, right? Because it's in simple harmonic motion there and back. And that is only the maximum, so it's only moving that speed briefly. Okay. So getting the acceleration maximum. Okay, so here we have, this would be 4, let's see, how should we best do this? I guess just 2 pi times the frequency, which is 0.13 hertz. Probably should be using some brackets instead of so many parentheses. We're going to square all of that and then multiply it by 0.4 meters. And what do we get here? Let me separate this so it's not makes it look a little bit better. Let's see. Let's go ahead and plug that in the calculator. Whoops. 2 pi times 113. So inside this bracket here, I'm getting 0.667 approximately. And this is going to be, units would be, a hertz is a per second, right? A hertz is a 1/2 second. So this is going to be 1 over seconds squared, or 0.667, yeah, over seconds squared. Okay, so anyways, we're going to end up getting meters per second squared, which is what we want. So we'll multiply this by 0.4, getting roughly 0.267. Ooh, my stylus isn't doing very well there. Sorry about that. And this is A max. Okay. There's our answer for acceleration max. Okay. So hopefully that's making sense. And if you don't like my explanation, obviously you can check with the book. But should be pretty straightforward if you watched the note guide last time. All right. Analyzing the motion of a hanging toy. It says a classic children's toy consists of a wooden animal suspended from a spring. All right. If you lift the toy up 10 centimeters and let it go, it will gently bob up and down, completing 4 oscillations in 10 seconds. What is the oscillation frequency? Okay. And then it asks some questions about max speed. What is the speed? Or when does it reach max speed? What are the position and velocity 4 seconds after you release the toy? Okay. So, this one's a little tricky. Let's see. So let's start here by drawing the situation. So we have a classic children's toy. I don't know if I can draw this. Oh boy. I was going to draw like a pony or something. I shouldn't have told you what I'm drawing. Now it's going to look even worse. Okay. Yep. All right. That looks pretty good. All right, so this toy is oscillating about equilibrium. So how are we going to draw that? Let's see. This toy is just so good. So we're thinking something like this. We got the spring right here, and it's starting. We lifted it 10 centimeters up. So maybe it started right here. And this is going to be 0. This will be equilibrium. And this distance right here is the amplitude. Right? And then it's going to oscillate from, say, this point right here all the way, a cycle would be to 10 centimeters below equilibrium and then back up, and it's going to oscillate back and forth, right? So it's going to go down and back for a cycle, right? And so it's going to, so I'm trying to say, let's see, so we have 0 right here, over here. How can I draw this? I don't think I like that. But right here we have the position +10, and we will also have the position -10, right? And it'll go back and forth about that equilibrium. All right. They start off by telling us the frequency. They say it completes 4 oscillations in 10 seconds. So the frequency is equal to the number of oscillations per second, cycles per second, right? So what it's saying then is 4 cycles every 10 seconds. So if we plug that in our calculator, we can see the frequency is equal. Let's see if I can just try and separate this a little bit. The frequency is equal to 0.4 hertz, or cycles per second. All right, that's what we're saying. Okay, so far so good. We got one of our answers right there. There's our frequency. When does the toy first reach its maximum speed? And what is the speed? Okay, so I think with this one, it's best to draw a graph of simple harmonic motion, and to see this. There is other ways you could do it, but I think this is probably the easiest and will make the most sense. So here we got our position versus time graph. Oops, I was hoping that was gonna. I guess it's about the y-axis, right? So I'm gonna call this its y position, and this will be time in seconds, and we'll say that this its amplitude is 10, so I'm just gonna say 0.1. Might as well make that switch, right? So this is 0 or positive 0.1 meters, and down here is negative 0.1 meters. And we're saying that it's going to start here, and this is just going to be a positive cosine wave, just like we had last time. Here's t over 4, here's t over 2, here's 3/4 t, and here's t right here. And we can see, let's see, by starting here, it's going to take this kind of path right here of simple harmonic motion. Whenever we have something oscillating, according to Hooke's law about equilibrium, we know that the motion is going to be simple harmonic. When there's a linear restoring force, we have simple harmonic motion. So we expect to see something like this. What is the period, right? What is capital T? I don't think we solved for that. So if we go back up here really quick, T is equal, whoops, all right, there we go. T is equal to 1 over F. So T then is equal to 1 over 0.4 hertz. Now, what is that equal to? I have no idea. I think it's about 2 point something. Divided by 0.4 is the 2.5? Yeah, 2.5 seconds is the period. All right, so let's go ahead and come down here. We can go ahead and jot in 2.5 seconds. Okay. We can also jot in, we can call this then 1.25. And what's a fourth of that, right? Divided by 4 is equal to 0.625. And what about 3/4 of that? So plus 2 or plus 1.25, 1.875. Okay, so, and then obviously 2.5 right here. So let me go ahead and erase this. This doesn't have to be there. All right, so we have these different time values right here. And the question says, when does the toy first reach its maximum speed? Well, we know its maximum speed is reached when oscillating on the y-axis, it hits equilibrium. So where is the first time it hits a position of equilibrium, which would be at 0, right? So that's what we want to know. And then coming down here, we can see that that would happen when the position is 0, which is at t over 4, which is 0.625 seconds. So when does the toy first reach its maximum speed? Would be when it's at equilibrium for the first time, and that would be 0.625 seconds. Now, what is this max speed? That's where we want to use our formula we have, right, that we just used a second ago. Vmax equals 2 pi f times the amplitude, and we can go ahead and plug in what we know there. So we have the frequency was, already forgot, 0.4. All right. Let's see. And the amplitude is 0.1. Sorry, that's hard to read. I'm running out of room there to write. So 2 pi times 0.4 times 0.1 is equal to 0 0.25 0.251, so meters per second. I guess I'll keep the 1 on there. It's probably wise. And this is our Vmax. So this is the speed, right? Because obviously the toy is moving downwards at this point, right? It started up and it's moving downwards, so this is its max speed. This is not its velocity. Its velocity would be negative 0.251. So I'll just write max speed. All right, good. So there's part B. And then finally, part C. What are the position and velocity 4 seconds after you release the toy? And I thought this was kind of neat. Something that the book did here. And I'm going to try and do the same thing if I have enough room. So what the book did is they went ahead and extended this, right? And made this 2t. So I know it's going to be a little bit off because I don't have a ton of room, but you can see that the time for 2t is going to be 5 seconds, and 2.5 plus 1.25, so this would be 3.75. And I think if we add 0.625 to 2.5, this is 3.125. And right here, 3.75. I'm just going up by 0.625 every time if you don't know what I'm doing. This is 4.375. Now the reason that we're doing this, right, is they say what are the position and velocity 4 seconds after you release the toy. So we can make a prediction, is what I'm trying to say by using this graph. Now obviously we want to be exact, but we can look at this graph, right, and predict, because this is simple harmonic motion, it just repeats. So we see something like this again, right? Obviously it's going to look a little skewed because it's all smushed together. Let me see if I can let me attempt to draw this. It's probably going to look awful, but let's see. It's my best work yet. All right. So we can see by looking at this what's going on at 4 seconds. We can predict, right? First of all, its position. Well, let's find 4 seconds. 4 seconds is in between 3.75 and 4.375, about halfway in between, we'll say. Maybe a little closer to 4.3, right? So maybe about right there. So this is 4 seconds. Okay, that's in highlighter. That's kind of weird. All right, right there. So what is happening with the toy at 4 seconds? If we follow it down, we can see that its position is negative because it's below 0, right? So we're predicting a negative position. And what about its velocity? Well, it just hit 0 velocity, right? It was going downwards right here. And then it hit 0 velocity right here where it had to turn around. Whoops, dang, what's that line doing? Let's try that again. So it's got a negative velocity, then it's got to turn around when it gets right here, and then it starts going upwards. So now it's going to have a positive velocity. I don't know why that keeps wanting to make a straight line. It's going to have a positive velocity at 4 seconds as it's moving back up towards equilibrium. So we're predicting a negative velocity or negative position and a positive velocity. Once again, this is for at 4 seconds. Okay, so good, pretty good, but not quite good enough, right? We need to know exactly. So to know exactly, what we'll do is we'll break out our equations, right? That I know we have in the textbook on page 447. And it kind of goes off the idea that we can write these position, velocity, and acceleration equations as a function of time, right? The first being was that our graph right here is a positive cosine wave. Because that's the case, we can write a position function, right? For its y position, y as a function of time is equal to the amplitude times the cosine of 2 pi f times t. We're not going to need that one, but if we think about that, right, we know that, and this is kind of given to us, right, but we talked about this last time, that we take the derivative of this, right, to create the next function, which is the velocity function. And I'm just going to keep it as Vmax, but we know this is a negative Vmax. And this is going to be a sine wave, right? A negative sine wave. So we have I'll draw it in a second, and this is going to equal 2 pi f times t. And then we take the derivative one more time, and we get a negative cosine wave. So we end up getting something like this. A of t is equal to negative a max times the cosine of 2 pi f times t. And once again, these equations are true for a Vmax of 2 pi f times the amplitude, and an Amax of 2 pi f squared times the amplitude. And these don't always have to be this way, right? This just worked out this way because we were given, right, if I come down here and draw it, right, we were given a y versus t graph where this was let me see if I can draw this, a positive cosine wave, right? And when that happens, the v versus t graph is a negative sine wave. Maybe I should draw those so they look so they're the same length. How about that? Maybe I can try. I'm not saying I'm gonna be able to do it, but I can try. That's a little bit better. All right, not a lot better, but a little better. And then finally, the acceleration. And these are based off each other, right? Meaning that the positive cosine wave, if the position wasn't a positive cosine wave, then velocity wouldn't be a negative sine wave. So they depend on each other, right? If position was a negative cosine wave, velocity would be a positive sine wave. And so it does depend. And position could be, say, a positive sine wave. And then, and if that was the case, then velocity would be a, what would that be? A positive cosine wave. Yeah. If I had a positive sine wave for position, then my velocity would be a positive cosine wave. And my acceleration would be a negative sine wave. But anyways, okay, so coming back to this, the last one here would be the inverse of, or the position function inverted, which would be a negative sine wave, or I'm sorry, negative cosine wave here at the bottom. Okay, so something like, something like that. All right, so this is what we're dealing with here, right? So positive cosine, negative sine, negative cosine. And that's why we're seeing these show up in the equations. They're all related. All right, we're seeing them show up right here. Okay, so good. Let's go ahead and solve then for the velocity as a function of time, right? What is the velocity at time equals 4, right? And I think we know, I think that's what it's asking us. Let me just double check the question. Oh, what are its position and its velocity? So we're going to need both. We'll need both, let's see, both this equation right here and that equation right there. So let me maybe insert another page here. Okay, so we can say then that y as a function of t and is equal, when t is equal to 4 seconds, right, is equal to the amplitude, which we said was 0.1 meters. I'm not sure why I'm writing in blue now, but that's all right. And here's where we got to make sure we're in radians. Right, that was one of the caveats that they said in the text, and you got to make sure for these equations to get the get the answer to be correct, right? And for its sign to be correct, for yeah, all right. Okay, so 2 pi, what is the frequency? I think we solved for that earlier. Frequency was 0.4 hertz. And we got to multiply that by t. So the time is 4 seconds. Okay, so once again, this is this. Let me see if I should write this in purple. This is what we're taking the cosine of, right? So we're taking the cosine of 2 pi ft. So we're taking the cosine of this right here. So I have to be careful there, because I'm just tacking numbers on there and forgetting that that's all inside the cosine. So we have, let me switch my mode here to radians. Okay, I think we should be good. Okay, so 2 pi times 0.4 times 4 is equal to 10. So what we're saying is this is going to become this is 10.053 rad right here, right? So okay, so if I do that, what I get is negative 0.809, and we're going to multiply that by 0.1. So we're going to get y of t is equal to 0 or negative 0.08. I'll put a 1 there too. 0.81 meters. So this is negative 8 centimeters, which is about what we predicted, right? Yeah, you figure it's negative 10 centimeters right here at the bottom. And so negative 8 centimeters seems pretty realistic, pretty spot on for our prediction. All right, and then finally we'll do our V of t. And this is going to equal our Vmax. I think we found Vmax already, right? Yeah, 0.251 meters per second. And we're going to multiply that according to this equation right here by the sine of 2 pi ft. And don't forget that negative sign like I just did. So there is a negative sign out in front. And that is going to be important, right? We expect it to be a positive answer, so I'm guessing when we take this sign here, right, we're going to end up doing some kind of we're going to get a negative answer. So we're saying we got 2 pi times 0.4 hertz times 4 seconds, right? 2 pi ft. And okay. So if we do that, once again, we're in radians here. We're taking the sine of this whole mess right here. All right. So what is the sine of that? Let's see. Let's see here. Sine of that. This is going to be the same as it was last time, right? So in both of these cases, I think this right here, this whole mess was 10.053 radians, right? Like we just said up here. And so we're just taking the sine of that. All right. That's going to give us a negative answer just like we predicted. So we're saying this is, let's see. This is going to be negative 0.251 meters per second times the sine of that was negative 0.5877. And there's no units on that, right? So what happens when we multiply those two? We should be getting a positive 0.148 meters per second. Okay. All right. So that's saying 14.8 centimeters per second. That, I guess, seems okay. What was the max velocity, right? The max velocity we said was that 0.25 or 25. I mean, that's 25.1 centimeters per second. So I guess I'm all right with that. I thought it might be a little fast, but I guess that seems reasonable. It's speeding up at that point. It's, yeah, but at least it's positive like we predicted. And that's about it. All right. Well, I think I'm going to go ahead and pause it there. And I don't think I'll add anything else onto this lecture. I think that'll be it. But these are just some sample problems out of the book. And from here, we'll work some of the problems at the back of the chapter after this on 14.3. So have a good day.